Hello, physics students. I'm going to give you some notes here about a mass oscillating on a spring. So there's two ways you can imagine this set up. One of them looks like this. So here's our spring, here's the mass. This could be right here, the position where the spring is not stretched or compressed. So we could call that like x equals 0. Or you could also have it set up like in the computer simulation that you did, where the mass is oscillating up and down. So both of those work. This one is a little bit easier to talk about because you don't have to worry about gravity. So here, you can imagine, I'm going to make a couple of dots here for when the mass is at these different locations. When the mass is here in the center, then you have a gravitational force on it down and a support force up. And there's no spring force. This is the force of support, not spring, because the spring is at the equilibrium position, right? X equals 0. So it's not stretched or compressed, so it's not doing anything. Here, when we're all the way at the furthest point to the right, we'll say that that's the positive direction because it's to the right. Of the same support force, same gravitational force. And then think for a minute about what direction the spring force would be when it's all the way over there. Did you think about it? And the force of the spring would be that way, right? The spring would be pulling it back. Sometimes we talk about a spring force as being a restoring force, meaning that it always wants to come back to its equilibrium position. It always wants to restore that balanced condition. So if you're over here to the right of that, then the spring wants to pull it to the left. And as soon as you get to the left of the equilibrium position, the spring wants to push it back to the right. And we'll just finish making that diagram here too. So this is the support force, gravitational force, and now if it's over here, the spring wants to push back toward the middle. And we know how big that spring force is. If we know that this is a spring with a spring constant K, then the force, magnitude of that force is K times X. Right. So let's see, what are the other things that we need to know here? We could make a graph of position versus time. I could think about what that might look like. Usually, this does not have to be the case, but we usually imagine that the spring has been pulled over or pushed to its maximum position, right, whatever its amplitude is going to be, and then we let go and it starts oscillating from there. So if you think about like what you know about sine and cosine and the shapes of those graphs, which one of those, sine, cosine, sine, or negative cosine, which one of those graphs would be the right one? Let you think about that for a second. And if at time 0 we started at that maximum position, it's going to start here, so that would be a cosine graph, right? And when I graph trig functions, sine and cosine anyway, I like to make those 4 little marks so I can map out the cycle of the function. So it would look like this, and then it would keep going as it oscillates back and forth. And this position here, this is its maximum at A. That's the amplitude. And this here is the amount of time it takes to go through one full cycle. We call that the period. All right. what would the velocity look like as a function of time? Well, we don't want to get too deep into like calculus concepts, that sort of thing, but we do know that the slope of position versus time is velocity. And you can see these points where it's turning around, like right at the very instant here, that's where we're letting it go. Well, that's going to have a velocity of 0 there. And here it's turning around, going from like the negative direction back to the positive direction, so as it turns around there, it has to have a velocity of 0, and then likewise again here. And it starts out going in the negative direction, and here it has like maximum negative slope. So that's going to look like this. And spoiler alert, it is true that if you find like the slope of a sine or a cosine graph, it is another sine or cosine graph. That is a fun calculus fact. We could mark on the vertical axis here, this is like the maximum velocity that's happening, well, maximum speed here, right? We could also think about the acceleration. Acceleration is the slope of velocity, right? So just using that same logic, we should be able to map that out real easy, because these are the places where we would have 0 slope, and this starts out with a negative slope, so it's got to be doing this kind of dance. So that looks like it's a negative sine, negative cosine rather. Right, and this would be the maximum acceleration. And oh, it's a little off screen there. Sorry about that. And then last, what about the amount of force? Sorry that I ran out of room there and I can't stack this one underneath. If you think about the fact that unbalanced force is equal to mass times acceleration, then these two graphs have to look exactly the same, except for this one is scaled up by a factor of m, right? If you took all the values of this and just multiplied by m, then you'd get this. But m is just some positive number, so that's just going to scale this graph. So it looks identical to the acceleration graph. And if we think about that for a minute, that should make a whole lot of sense that when we start it here, that is maximum force because we have the spring extended the maximum amount right when we let it go, and that force is going to be in the negative direction. So it's like the biggest force that we get in the negative direction. And then when it makes it back to equilibrium, when the x is 0, well, there's no spring force right there. And then the spring force starts to act in the other direction, the positive direction, until I get maximum there and so on. Right, so the positive negative of this is just telling me what direction, and this is just telling me how big. So that's what those graphs look like. And then one more thing. I just have to, well, there's two ways we can get at the next fact. In the simulation, which you should have completed by the time you're looking at these notes, made your graphs and all that, I think what you should have found, I'll recap the results there, is that period is directly proportional to the square root of mass. That period is also inversely proportional to the square root of k, and amplitude doesn't matter. Doesn't affect the period. Which is pretty interesting. So that means we're expecting the equation for period would be something like period is equal to, it's directly proportional to m, inversely proportional, sorry, the square root of m, inversely proportional to the square root of k, and that there's some constant of proportionality there. And it turns out that constant is 2 pi. The way to sort of theoretically demonstrate or derive this result involves second semester college calculus. So it's just like beyond us right now. And we got pretty close to this just by doing a little bit of experimental messing around. So this is just a fact that we need to know about the period of a mass on a spring. So back to this situation here. If you know what the mass of our block is, and you know what the spring constant is, then you can say, okay, I can use this formula to figure out what the period is, how much time it will take to go through one full oscillation. And I do believe that that is all you need to know at this point.